Alright, so chapter 4 was our introduction to forces. And we really did only limit ourselves to forces that were acting like in one dimension. We didn't have any perpendicular forces or anything like that. So when I went through that chapter, the first thing that jumped out at me was the distinction between contact forces and field forces, right? So you want to know that distinction. You want to remember our three examples of field forces: our gravitational forces, our electric forces, and our magnetic forces. We drew a ton of free body diagrams in chapter 4. So when we did our free body diagrams, we either drew our object or a dot to represent our object, whatever, and then we drew arrows to represent each of the forces that was acting on our object. Right? And our arrows always start at the center of the object and then point in the direction that that force is pushing or pulling. So maybe we have like a weight pulling down on something and a normal force pushing up. If there is no net force acting on the object, if it either has a velocity of 0 or at least a constant velocity, then we would have to make sure that our forces are all being canceled out by other forces. But we definitely should expect to be drawing free body diagrams. We met all of Newton's laws in chapter 4. But the first one was Newton's second law. Newton's second law was the one that related acceleration and net force. Right? So we said if there is a net force, that causes an acceleration. And we did quite a bit of work on quantifying that relationship. And net force, is just our fancy name for the sum of all of the forces that were acting on something. Newton's first law was the one that says an object will keep its state of motion. So something sitting motionless is going to keep sitting motionless unless there's an unbalanced external force. Something that's already in motion, like if I throw my marker, will keep that motion unless there's an unbalanced net force. In this case, there was an unbalanced or external force. That was the pull from the Earth. So it did accelerate down towards the ground. We did meet a couple of other terms. Inertia was a term that isn't a quantitative thing, it's a qualitative thing. It's the tendency for an object to keep its motion, and that is not a force. Right? If something's moving, it will keep moving due to its inertia. We don't need a force to keep something moving. And then equilibrium was just a word to describe when the net force was equal to 0. There actually is more of chapter 4, but were there follow-up questions on that first stuff from chapter 4? Okay. And then we got into Newton's third law. Well, actually, we got into Newton's second law a little deeper, and then Newton's third law. So we did talk about your weights, which we said was just a special case of Newton's second law. And then we did talk about scales, that all scales measure weight. If they say they're measuring mass, they're lying. Even though if they're manufactured to work on Earth, they're probably okay. We discussed apparent weight. We said sometimes you can step on a scale and it's going to show something other than your true weight. We would call that apparent weight. One of the instances of that was being on an elevator that's accelerating. We will get an apparent weight that's different from the actual weight. And we did calculations involving elevators. I think that was one of the first YouTube videos we put up because that was our first somewhat difficult type of calculation. We met drag force at the end of chapter 4. That was the air that the molecules of a fluid exert on an object that's moving through the fluid. That's always against the velocity of our object, or at least as long as we don't have a wind or a current, it's directed opposite the velocity. And then we said due to this drag force, we could have a maximum velocity for a falling object, and we called that the terminal velocity. We met Newton's third law then at the end of the chapter. Newton's third law was this thing that said that forces always come in pairs, right? We need two objects to be pushing or pulling on each other. And if the first object pulls on the second one automatically pulls back on the first one with the exact same amount of force, but in the opposite direction. And then we met normal force for the first time. I don't think we really need to review that, other than to say that we did have those few times when the normal force was not equal and opposite to the weight. Chapter 5 was also looking at forces, but now we were looking at them in 2 dimensions. So other than being in the same direction or opposite directions, we started off with dealing with vector quantities and how to combine them it was super easy if we had two vectors that were in the same direction. Like if we have a displacement of, I don't know, 2 meters east, and then another displacement of 5 meters east, we were able to literally just sum those two values to add the magnitudes together. If the two are in opposite directions, right, because they're vectors, the direction is important. So you'd have to assign one of these to be negative and one to be positive, and then you would still just add them. So you either add 2 to -5, or you add -2 to +5, whatever, right? It's still just addition. But then when the vectors pointed in perpendicular directions, we had to use a different process. The process that we used if they were perpendicular was to sketch one of the vectors, and then sketch the other one, starting from the head of the first one, right? And then we sketched on our resultant from the tail of the original one to the head of the final one. Sorry, that didn't really line up. So like this was vector 1, this was vector 2, and this was vector 1 plus 2. We used our Pythagorean theorem to find the magnitude of that resultant, and then we did have to use our trigonometry in order to find the angle. But we typically weren't able to just report that angle as the direction because we had our coordinate system, which had 0 degrees and 360 degrees being the same thing as east, 90 degrees being the same thing as north, 180 degrees being west, and then 270 degrees being south. So for this example, whatever the heck this angle is, we would have to add that to our north, add that to 90 degrees in order to get the absolute direction of that. Sometimes we have to subtract that as well. Questions about same direction, opposite direction, perpendicular before we get to other? Okay, other were our examples where maybe we had, a northward force, that doesn't even look north, that's fine. And then something that wasn't perpendicular or the same or opposite, right? And then what did we use to find the magnitude of this resultant vector? Law of something. Which one was it? Law of cosines. That's right. We used the law of cosines to find this, which looks a lot like the Pythagorean theorem, right? If this is A and this is B and this is C, the law of cosines says something like C squared equals A squared plus B squared minus 2AB cosine theta, where theta is always the angle opposite the resultant, right? So we use the law of cosines to get the magnitude of that, and then what did we use to get the direction of that? Law of sines, right? And I did add the law of sines onto your equation sheet. That was one of 2 changes that I made when I emailed it to you last week. Right, so if we have other than perpendicular or same or opposite, then we can use our law of cosines and law of sines. The other piece of vector math that we did discuss was finding the components of a vector. We had to do this all the time when we got to projectiles in chapter 6. Right, if we had an initial velocity that was at some angle, then we frequently had to split that into a horizontal and a vertical piece, right? So I think we probably remember how to do that. We would need a direction, I don't know, that looks about maybe 38 degrees. Maybe the combined initial velocity is 12 meters per second. So we can just use our trigonometry. We need to use sine to find the vertical part of that and cosine to find the horizontal part. We were fine with that. The only other thing in chapter 5 I think that we did was friction. So we did have 2 types of friction we dealt with. We had kinetic friction if the objects were sliding or skidding past one another, and then static friction if there was no relative movement between the 2 objects that were having friction between them. We had an equation that we used to calculate the frictional force. I'm giving a generic form, right? But it was the coefficient of friction multiplied by the normal force. What else do we need to say about that? In these problems, we were often given the mass, and then we did have to calculate the weight to recognize that the normal force would be the same magnitude as the weight. Any other questions pop up from you guys about dealing with vectors or the friction problems? Okay, chapter 6 was the only other thing I wanted to bite off today. So most of our time in chapter 6 we spent on projectiles. And we did only have those 2 different types of projectile problems. We had the one type where we stood up high and threw something horizontally. We had the other type where we stood on the ground and threw something at an angle. We had extreme similarities between our two types of problems, but we did end up using slightly different equations for the two types. The most important thing for these is that we have to keep our vertical and horizontal stuff completely separate. Okay, we can use whatever motion equations we want to solve these problems, but we have to use them either just vertically or just horizontally. And then the other thing in chapter 6 that we spent a fair amount of time on was circular motion. Okay, so if we had things not spinning, but traveling in circles, one of the really important things I can remember that we did talk about the direction of all of our vectors. So both the centripetal force and the centripetal acceleration of our object moving in a circle always points in towards the center of that circle, whereas the circular velocity always points tangent to the circle and perpendicular to the force and acceleration. We had some special equations for circular motion, I think most of which are on your equation sheet. The way that we commonly found the circular velocity was to use the circumference of the circle and then divide that by the period, the time that it took to go around once. For centripetal acceleration, we sometimes used v squared over r, and then sometimes we shoved this equation in for v, and ended up with 4 pi squared r over t squared. And then for the centripetal force, we only ever used Newton's second law. We only ever multiplied the mass by the centripetal acceleration. Other questions about chapter 6 stuff? Okay, so now if you have kind of stopped paying attention because you remembered all that, pay attention again. So in terms of logistics for our midterm, it is the very first midterm of the cycle, right? It's exciting. So it's from 8:30 to 10:30. This is wrong. It is not in the media center. It is in the multi-purpose room. Oh, come on. All right, so it's in the multi-purpose room. Expect assigned seats. Did you guys do the PSAT in the NPR?
Media center.
You
Well,
did
half
the
and
media
half.
center. Did you do, have you ever done a test in the NPR where you had assigned seats?
Yeah.
What, and of course bio?
Yeah.
Great. So expect something extremely similar to that. Like where it'll be the table set up on the wall. I'll probably even try and get it out to the block, whatever teachers you'll be in before then. And you'll have like your name with the table number and then A, B, or C, and that matches up with the diagram, right? So expect assigned seats. There's no way I could, have enough calculators to make all of you use one of my calculators, so you are going to be allowed to use your own. Obviously, don't program anything into it, don't have anything written on it, and I'm not allowing you to use graphing calculators. I know that non-graphing calculators, you can program stuff into those also, but it's a lot harder, right? So non-graphing calculators only. Borrow one from a sibling, right? Borrow one from a friend that doesn't go to biotech, but non-graphing calculators only, and don't have any other electronic devices on them. Right? Phones, Nooks, Kindles, iPod touches, like whatever. No other electronic devices. If I walk around and see a phone sticking out of your pocket, I'm taking it, I'm giving it to Dr. Eno, and telling her that you violated our testing procedures. All right? No other electronic devices, period. Anticipate no pencil sharpener. I have absolutely no idea if there's one in there or not. Probably not. If there is, I don't know if it works. So be prepared for no pencil sharpener. You are not to leave your seat for any reason during the test or after, right, until the announcement comes on at 10:30 to go to lunch. So don't ask. I don't want you to poop your pants. So if you really have an emergency, like you're gonna go, but then you're not like coming back and taking that midterm. You'll have to take a makeup midterm. What else? It's a 2-hour exam period. I hope that you're not going to be frantically using all 2 hours to take the test. Probably some of you will finish quite a bit early, so it's okay with me if you do have like a non-mathy or sciencey book underneath your seat that you can use. That shouldn't be notebooks, right? But like a real book, that's fine with me. But you would only take that out if the proctor collects your stuff early. I think, that's actually all that I had. What am I leaving out? What other things do we need to know before Monday? Yeah, Laura.
So, we can't bring study guides to class?
No study guides. It's book only. It could be a textbook for a class that's not math or science, but no study, nothing that's not like published by like a publishing company. I don't think you're going to have that much extra time in there. Any other issues, anything else that I'm kind of leaving off? Okay. There are going to be 2 different versions, so the proctors should be instructing you to mark like your version letter on your Scantron and on your line paper, but just know that you are going to have to do that. If you don't, and I guess wrong, at a minimum, it's going to make me upset, and maybe subjectively that will affect some of the marking of your questions. All right, that's all that I could think of. Anything else pops up, let me know. All right, where does that leave us? Torque. We're going to get to it. Yes. All right. I love torque. It's one of my favorite things, actually. It really is. Is it something we've heard of? Yeah?
Cyrus did it.
The what?
Miley Cyrus did it. He made shoes torquing.
Is it spelled the same?
Oh, absolutely.
No? But now I don't. So I've heard of this, the torque before. I don't know what it is. I haven't seen it to my knowledge. But I would wager, I might lose, but I would bet that it does involve torque. And you can tell me once we talk about it.
I guess sort of.
So torque does not always, torque probably always does involve center of mass. So yeah, on our snow day last week, I did send you guys a short video about center of mass. It is my expectation that you watched that. I will have some more to say about center of mass, but I don't know that that'll happen today. Now, chapter 8, I think, was rotational motion. And we spent very little time doing the first chunk of rotational motion. But we did spend some time, right? This was things that were spinning. And one of the majorly important things that we said was that everything that we said about linear motion, like moving in a straight line, had a spinning analog, a rotational analog, right? So we had like distance, I gotta be careful when Burton's gonna yell. Distance had a rotational analog of angular displacement, which had a symbol of, I might even have this wrong, either phi or theta, I always get them messed up. Speed, velocity, whichever one you want to talk about, had a rotational analog called angular velocity, right? That had a symbol of a lowercase omega, which is kind of like that curvy W. Acceleration had a rotational analog that was called angular acceleration, and it was a lowercase alpha. We talked about the units that we might measure all this stuff in. Really, truly, the right unit to measure this in is radians, but I don't care. We can use our degrees, we can use our revolutions, whatever. Angular speed should then be radians per second, or degrees per second, or revolutions per second. Angular acceleration should be radians per second squared, or any of those numbers, right? I'm not going to get all uptight about that. And I think that's kind of where we left off with rotational motion back when we did it. So we have dealt with other variables besides these 3. Surprisingly, not too many. What are the other variables we've dealt with besides these ones? Linear. None. Force. What else? Momentum. What else? You skipped one from in between those 2. Velocity we got. Oh, come on, it was just on your test, like every single problem. Mass. Oh, time also. Time actually doesn't have a rotational analog, it's just time still. Right? So time is kind of the one thing that doesn't matter what type of motion we have. So all of these things have rotational analogs also. The rotational analog of force is indeed torque. All right? Now torque has, its symbol is a Greek letter tau, kind of like a backwards, like a mirror image capital J, right? There is a rotational analog for mass that we're really not going to deal with at all. It's called moment of inertia. It has the worst name of anything in physics. Momentum has a rotational analog. It's called angular momentum. But we don't care about those ones. We do care about torque today. So this whole intro was just that torque is our rotational analog for force. And it does involve force. It involves something else though too. And what torque really is doing is controlling how effectively a force is going to cause or is going to make something rotate. Right? So in order to change something's angular velocity, you do have to exert a torque on it. And the amount of change that you get, right, that's dictated by our torque. So torque has like really 3 factors that control how large it is. There's kind of only 2 if we're smart about it though. So torque has both how much force we're using to make the thing rotate, and it also has a factor for where that force is applied. What's this orange thing supposed to be? Can we even tell? Yeah, it's a wrench, right. So you use wrenches to either tighten bolts or to loosen bolts. And this diagram shows 2 different forces being used. Let's see. Lefty, loosey, righty, tighty. So these forces will be trying to loosen the bolt, I think. Is that right? I think so. So we have one force, force A, exerted here, and one force, force B, exerted here. Which one is going to make it easier to loosen the bolt? Right, so I guess you could say A, you could say B, or you could say like exactly the same. So I heard a couple people say B. Raise your hand if you think B. All right, quite a few. Raise your hand if you think A. Maybe a few of you thought about it. And then raise your hand if it really doesn't matter. So a few people saying it doesn't matter. I think it does matter. I think B is going to loosen the bolt way more easily. And let's see if we can sort of demonstrate that. Who should we pick on? Yeah, we always pick on Henry.
Yeah, I'm used to it.
So everybody come on up here. We'll decide who we're going to pick on. You're going to stay up. Yeah, so we're just going to kind of stay like up. I want everybody up in the corner. So you can come up here too. All right, did we make a decision? I vetoed Henry. Alex? Burton? Hannah? Oh, Hannah's got a bunch of them. All right, come on, Hannah. Do you mind? All right, great. So Hannah's gonna torque the door.
Wait,
So right now there's actually a few torques acting on the door. In fact, there's 2. There's a torque up here because this mechanism up here is designed to actually pull on the door to close it, right? And so it's exerting a force kind of this way. It's exerting it here, so it's making the door want to rotate. And then there's an equal and opposite torque applied down here by the ring stand base. It's not a ring stand base, it's a, whatever, it's like a base. Let's get rid of it. So I got rid of that. Alright, so Hannah's going to come over here, and she's going to act like the base, right? So, but she's going to, you right-handed or left-handed? So Hannah's right-handed. I'm going to let her use whatever 2 fingers she wants, but I want her to use them like all the way over here, and she's going to push on the door and try to keep it open. Alright, you ready? Well, no, you're not going to use your foot. I just don't want it to close yet. So go ahead and get 2 fingers, but all the way over here. And then, like, don't end up breaking any fingers. So, like, don't push so hard that your fingers are going to, like, break. All right? In fact, why don't you do it over here first, just to get a feel for it. So 2 fingers here. And yeah, you have to, you can feel the door pushing on your right. All right, so now you're going to move your fingers over here, and the same thing. Well, all the way over here. Keep them together. All right, good. So it mattered. Over here, she didn't have any trouble keeping it open. Over here, it was really, really difficult. I want you to go all the way out here, too, and see if that feels different. Easy, right? Yeah, easy. All right, thank you. So it really matters, like, not only how much force you're applying, but the placement of that force is definitely really important. Questions about that before we kind of see what else we have time to talk about? All right, so let's sit back down. We need the base. And we need Julia as well. So is there any rotation occurring with the torquing?
Well, I mean, we said
No?
variation
Okay.
of- It does seem like-
All right, but it seems like the answer is no. All right, so I would have lost my bet. You should have bet me.
And there is.
Now, I said earlier that we have about 6 minutes. I said earlier that there's sort of 3 things that affect how much torque is getting exerted on something to rotate it. But I said really, if we're smart about it, there's 2 things. We can move all the way out on this wrench. Let me get a real wrench. We can move all the way out on that wrench and be really stupid and exert and have a very difficult time opening that bolt. So here's a bolt right here at the end of the sink. I actually hate these things. I don't know why we have it. I like the sinks, but I don't like this nozzle at the end that makes the water come out super fast. I don't know why we have it. I've removed a bunch of them from this room. I guess I removed this one, that one over there. I guess I've never removed this one. No, if I don't have that on, it actually comes out pretty slowly, and it's a larger flow rate if I take this off. So I don't know why we do that. So I don't need a whole lot of force. This isn't stuck on, so apparently I have removed it a few times. I can actually get it pretty. Let me get it kind of tight, and I don't have to exert much force. All right, hinge, whatever. I don't have to exert much force to get that thing to rotate. But I could be super stupid and exert a larger force and not have it rotate. What would I do? And on the end, or I could be stupid and do it up here. But how could I do it on the end and have it be really, apply it really stupid? Jesse?
Could you like push the wrench down?
Down would be pretty stupid. But also just like directly towards you would be pretty stupid. Right? So it's not just how much force and where, it's also like what is the direction of the force. So you really want to do it perpendicular to the wrench to maximize the effect that you would have on the rotation of the thing, right? So I mean, torque is a quantitative thing. We're not really going to solve problems with it, but I don't even have it in the notes because I didn't want to go there. But torque technically is equal to the force times a variable called the lever arm. The lever arm is just how much distance is there between the axis of rotation and where we're applying the force. And then we do need a term to